Hello and welcome once again for a practice problem. This time we're going to do the ideal gas law. So we're going to check the applicability of the ideal gas model for each of the following scenarios. And what you need to recall is that the compressibility ratio has to be approximately equal to 1 for the ideal gas, because obviously if it's equal to 1, then that means that PV is equal to RT, which is the ideal gas model. So there's a couple of ways that we could go about this, but I'm going to use the compressibility table figure that we have here. This is figure A1. And so what I'm going to need then is I'm going to need to find the reduced pressures and temperatures in each of these cases to figure out if this is applicable, if it's approximately equal to 1 or not. Okay, so to find the reduced pressures and temperatures, we just need to divide the pressure by the critical pressure and the temperature by the critical temperature. So then we're going to find the critical, notice that we have these in English units here, pound-force per inch squared and 600 degrees Fahrenheit, and similarly for these. So for the two first parts of this problem, so I'm going to go to table A1E to find the critical pressures and temperatures. The critical pressure and temperature in these two cases appear for water. Okay, so at 600 degrees Fahrenheit and at a pressure, oh, sorry, I don't actually need to know these details, right? I just need to know for water. Going to the table, we find that for water, the critical temperature, Tc, is equal to 1165 degrees R, which is in the Rankine scale, so we're going to have to be careful here and actually do that conversion from Fahrenheit to Rankine. And Pc is equal to 218 atmospheres, which we're also going to have to do a conversion there to get it into pound-force per inch squared so that I can use these. Okay, so what we can do then is we can recognize that the Fahrenheit, so if I have a temperature in Fahrenheit to Rankine, I'll just call it T rank for now, is equal to T Fahrenheit plus 459.67. Oops, 67. Okay, so if we do that, then what we find is the temperature that we were looking at, which was 600, that's going to be 600 plus 459.67, which is going to be equal to 1059.67 degrees Rankine. And so our reduced temperature, TR, is going to be equal to 1059.67 divided by the critical, which was 1165. And this is going to be approximately 0.91. So I'm just going to round it to 0.91. And obviously, we're reading off of a table here, so we're not going to get extremely accurate anyways. Or we're reading off of the figure here. So then the reduced pressure in this particular case is going to be the 900 and divided by, but now we have to convert this 218 atmospheres to pound force per inch squared, and here the conversion is 1 atmosphere is equal to 14.6959 pound force per inch squared. So obviously that means that we have 14.6959 pound force per inch squared per atmosphere. So we just have to multiply that. So down here, what we're going to get is 218 atmospheres times 14.6959 pound force per inch squared per atmosphere. And if you work this all out, it becomes approximately 0.28. Okay, so that's our reduced pressure and our reduced temperature. So now we can actually go to our chart here, and we're going to find approximately 0.28, which is, roughly right in here. And we're going to go up to our reduced temperature of 0.91. Well, that's going to be slightly above this line. So I'm just going to map it out here, somewhere right here, and it's going to come up just above that line. And that's about 8.87, right? So Z is approximately equal to 0.87, and that's not going to be close enough to 1 for us to consider. That's 13% away from being 1, which is a pretty big difference. So we're gonna say in this particular case, water at this temperature and pressure is not going to be considered an ideal gas. Okay. Now we can go back and read off of the tables again, so that we can see that, and we can go through this whole process again. So what I'm going to do, I'm not going to read the values, though. I'll just have those prepared. I have those prepared already. So at 100 pound force per inch squared and 600 degrees Fahrenheit, what we find, reading off the table again, is that PR is approximately equal to 0.03, and TR is still just, the temperature obviously didn't change, so that's still just 0.91. So if we come over here, now 0.03 is really over here somewhere, and for 0.91, if I'm coming over here, I might say that that's like 0.98 going up here. Going up here, the line goes right about there, so maybe around 0.98 is my compressibility factor in that scenario. So obviously approximately, that's pretty darn close to actually to, it's about 2% error, right, for being to 1. So we will say appropriate in this case. So we will say that we could apply the ideal gas model to water at those pressures and temperatures. And then we can do the same thing for nitrogen, although this case we're going to change from table A1E, we're going to use table A1, because this one was given in in SI units, and just remember to convert Celsius to Kelvin when you're doing this, just so that you get the proper reduced temperature there. But what we find is that the reduced temperature is approximately equal to 1.1, which is on this still on this graph, this chart here. And for the first scenario, 75 bars, the reduced pressure is approximately 2.24. That's roughly what I got. 2.24. So that's actually not even on this chart here. It's on it goes way off onto the next chart. But if you go on to that other chart, what you find is that Z is approximately equal to 0.42, which is obviously a long ways away from 1. That's a big difference. So not applicable. And still for the same TR, but in the case of pressure at 1 bar, what we find is that the reduced pressure is approximately equal to, again, 0.03, which is the same one that we had before, but this time the TR is 1.1, which obviously is above where we were before. In fact, it's way up here. Let me just put it in purple here just so we can see that. It's way up here. So that one actually is approximately 1. That one I would say is approximately 1, which obviously means it's applicable. That's all that I have for this video. Hope to see you again soon.